name is Schnegg, and I will introduce you today into EPR spectroscopy. I got very strongly wired here. Can you all hear me? Are these connections working well? So, super. Thank you. You got already quite a load of magnetic characterization techniques and its background. I hope you are not feeling like this now, but in order to give you an idea of why we are doing all these things, I wanted to zoom out a bit and remind you what the magnetic resonance perspective actually is. Shown here is the protein myoglobin, a paradigm protein, the first which was crystallized, and the people who did this were awarded with the Nobel Prize. In crystallography, as you all know, we determine the positions of atoms geometrically relative to each other. However, in magnetic resonance, we use a different source of information, and this source are spins in a sample. Shown here is, maybe you see this in the background, is again the heme cofactor of this myoglobin, and the information which we are exploiting in magnetic resonance are interactions between nuclear spins, for example here protons, 14N, 17O, with each other, with an external magnetic field, and with electron spins from unpaired states in our sample. And this is the information which we get to derive information on the electronic structure, the also geometry, and many other things which I will outline in the coming, I think we have 1.5 hours. I had planned to talk for 1 hour and then we make something like a 5 minutes break and continue, because I understand that it's already quite late today. What do we get from evaluating these pieces of information? Well, we can quantify spins in our sample. This is particularly important in electron paramagnetic resonance because it allows us to count unpaired electrons and therefore determine, for example, how much of the iron which you have in your sample is in a particular oxidation or spin state. Even more important probably is the information which we derive from a line shape analysis, and about this I will mostly talk today. From this we can determine the type of paramagnetic specimen, its oxidation and spin states. The two are of course closely related. The coordination geometry, the nature of ligands, for example, which atom is coordinating to a metal site, the delocalization of spin in our paramagnetic site, and coupling to neighboring spins. This is important, for example, to derive structural information by measuring the distance from spin A to spin B. And to give you an overview of our EPR, our samples which are typically EPR active, I put here a not complete list of samples which are oftentimes paramagnetic. These are reactive oxygen species. This is very important in medicine. Protein cofactor radicals, for example, tyrosines, porphyrin, flavins. Paramagnetic transition metal ions in both synthetic compounds but also in proteins, of course. Important examples are the different oxidation states of iron, cobalt, copper, titanium, molybdenum, and some others. A very important in, for example, photovoltaic research or organic electronics are light-induced triplet states and radical pairs, because by measuring these states one can determine electron transfer processes and the partners who are involved in these processes. Material defects like dangling bonds and tail states or vacancies are oftentimes paramagnetic. Conduction electrons are paramagnetic, however, oftentimes very difficult to detect because they have very broad lines, but this can also be a source of paramagnetic resonance. In addition, one can add certain molecules to a sample to make the sample paramagnetic. This can be, for example, a spin trap. These are small molecules which trap short-lived radicals and form adducts, which can be then measured on a longer time scale, and oftentimes the line shape of these adducts are sensitive to the radical, to the initial radical attached to the trap. In addition, spin labels are site selectively attached, to example, to proteins to measure distances of subunits in proteins. These interactions are relatively weak, as you may have heard already today. I think Frank also already mentioned this. The interaction energies are corresponding to frequencies in the kilohertz to terahertz range. Nuclear magnetic resonance is typically in the megahertz range, whereas EPR is mainly in the gigahertz range, and this corresponds to relatively low temperature which this corresponds to cryogenic temperatures, and therefore oftentimes it makes sense to cool our samples, as I will outline. You have seen these properties already. Electron spin is the angular momentum of electrons. It's a purely quantum mechanical property. The electron spin is associated with a magnetic moment, which is determined by the Landé G factor, which is approximately 2.0023 and has many additional numbers which have been determined with great accuracy for the free electron. And the Bohr magneton, I wrote here both conventions, μB and beta E, both are used and just mean the same. And this property is a product of the charge of the electron, the Planck constant, divided by the mass of the electron and the velocity of light. As you have already heard, magnetic moments orient in an external magnetic field, and the energy levels which we determine from and the resulting energy levels can be described by a equation which is shown here, which is the spin Hamiltonian. And today in the morning you got already very extensive introduction into this equation, and it's indeed super important and covers most things which we are dealing with in EPR. Energy splitting between spin up and spin down for an S1/2 particle. It can be then calculated by the eigenvalues determined from this spin Hamiltonian, and the energy difference between energy levels is what we measure in magnetic resonance, or in this case electron paramagnetic resonance. Well, I already told you that electron spins orient in an external magnetic field, and there's an energy difference, as I have already mentioned, between spin up and spin down, but due to the fact that this energy difference is relatively small, already at cryogenic temperature there is also an excitation to higher lying energy levels, and this spin population increases by increasing either the external magnetic field, which increases the energy difference, or by decreasing the temperature. The spin population of the levels n plus divided by n minus can be described by Boltzmann statistics, and this exponential function contains the spin energy level splitting, delta E, divided by the Boltzmann constant multiplied by the temperature, which means, as I already mentioned, the higher the energy splitting, or the deeper the temperature, the higher the polarization. And this is important because this determines how much microwave is absorbed in our sample and increases therefore the signal which we are detecting. Now, magnetic resonance. Up to now we just applied a magnetic field to our sample and oriented our spins within this external magnetic field. We now apply a microwave field with an energy which exactly matches the energy difference between spin up and spin down orientation. And by applying these resonant microwaves, or in the case of NMR, megahertz radiation, we excite electrons and change the population in our spin system. And if we now switch off the external magnetic field, our system will start to irradiate microwaves exactly with the Lambda frequency, and this radiation decays with a characteristic time. And by measuring this signal and Fourier transforming it, one can obtain a magnetic resonance spectrum. This is what is done in NMR. All the NMR machines, even the tabletop ones nowadays, which we are using, are measuring either echoes or free induction decays, applying a Fourier transform, and zack, you get the spectrum. This is very convenient, doesn't need any field sweeps, is super fast. It's benefiting from an effect which is called multiplex effect, and the introduction or the employment of all the possibilities which you have get from a free induction decay was shown by Richard Ernst, who received the Nobel Prize for employing free induction decays and echoes and pulse NMR in its full width. And it's also the basis for. It was later also the basis for the development and invention of nuclear magnetic resonance imaging. I don't know if you've ever been exposed to an MRI scanner. There are fields changed in the scanners, but they don't sweep the external magnetic field. It's a pure FID technique, and this would not be possible without FIDs. Now I have advertised the use and beauty of FIDs. However, in EPR we usually can't. And this is due to the fact that our signals decay so fast that our detection technique, which is nowadays available in the gigahertz range, does not allow to detect FIDs with the necessary accuracy. And in addition, we cannot make our microwave pulses short enough to fully excite our spectrum. Therefore, we have to resort to another technique, which is even the older one, and also NMR has previously has been recorded by this technique. This is called continuous wave electron paramagnetic resonance, and as you may guess, from continuous wave we irradiate continuous radiation on our sample while sweeping an external magnetic field, and in the moment we hit, therefore we change the energy splitting of our spin, and in the moment we hit this fixed microwave energy, we detect an absorption spectrum. This is usually detected as a derivative spectrum, and why this is I will explain in a minute. First I will show you how the first EPR spectrometer looked like. This is approximately now 81 years ago that Yevgeny Savoysky set this up in Kazan in the Soviet Union. Surprisingly, it still has most of the components we are still using in a EPR spectrometer. It has a large magnet, a resonator, and a microwave bridge. And here on the right-hand side, the scheme of such a spectrometer is shown. We have a source and a detector, sweepable external magnetic field, and a thing which is called resonator. And this resonator is placed in the external magnetic field, and in this resonator our samples are immersed. I will explain in 2 or 3 slides why this resonator is needed, but now I would like to refer to these additional loops here, which are additional coils, and these additional coils provide a modulation of our microwave field. This is a research grade spectrometer. You will see one in the lab tutorial. Coming back to the field modulation, this vector is the external magnetic field, which is swept over time, so it's getting bigger and bigger, but on top of it we apply a fast modulation in the kilohertz range. And what this is doing is that we scan along this axis, and at the same time we modulate our field, and this modulates the resonance signal which we get when we get into resonance while sweeping the external magnetic field. And the amplitude of this modulation is the bigger our modulation is. And since this is changing sign, when we go through 0 we get a derivative spectrum from our lock-in detection. Why we are doing this? Well, this can significantly boost our sensitivity, and is therefore routinely used in CW spectrometers. This detection technique is called lock-in detection. It actually works with any effect modulation you may think of. You can also modulate light and use a lock-in detector and so on and so forth. There's some technical details which you should keep in mind, which are arising from lock-in modulation. Our signal gets the bigger, the larger our modulation is. However, by increasing the modulation amplitude, we also increase the line width, and beyond the natural line which we would like to detect. And you can see this quite well here. Here are two peaks in our spectrum. The signal gets bigger and bigger. However, here we have lost our resolution, and this is oftentimes not wanted. Therefore, and this is a sample-specific parameter, therefore you have to adjust it on a particular sample. If you have very broad lines, you can afford very large modulation amplitudes and boost your signal. However, if you have tiny splittings, then you have to be careful with your modulation amplitude. Another technical aspect of EPR, which I would like to mention because it strongly determines what kind of samples you can measure in your spectrometer, is the EPR resonator. This is in most cases, a hollow structure which has resonances at the frequency you are measuring. And here, for example, such a resonator is shown. This thing here is the microwave transmission line which is attached to the resonator, and this picture here is a cross-section through such a resonator. Shown in blue is the electric field component of the microwaves in the resonator, and in red is the magnetic field component. And this explains why we are using such resonators. First, we would like to increase the magnetic field component of the microwave on our sample, because this increases our signal. And in addition, we would like to separate the electric and the magnetic field, because if you are not doing this, then for many samples we would just heat our samples. We are doing measurements in the gigahertz range, and this is very close to what you use in a microwave oven, and therefore not very suitable actually for spectroscopy, and therefore we have to play this trick. And then we placed our sample in the magnetic field component. The resonator is characterized by a property which is called Q factor, and this is just the fraction between the resonance frequency and the bandwidth of this resonant dip. You see this dip in many spectrometers when you are adjusting the spectrometer. And as I already mentioned, the resonator strongly determines what kind of samples you can put in your spectrometer, because they have to fit in your approximately 4 mm sized EPR tube, and this can be, for example, crystals. You can rotate the crystals in the resonator. I'll show an example later why this can be very useful. You can just fill powders or liquid and frozen solution. If you are using liquid solutions, you have to use narrower EPR tubes because they damp the microwave field. Sample concentrations are typically in the micromolar to millimolar range. Like in many spectroscopies, the more sample you have, the stronger your signal gets, but you may get coupling between the neighboring electron spins, and this makes your line width broader and may blur your spectrum. EPR spectrometers nearly always come with facilities to cool the samples, and this is due to the fact that generally going to lower temperatures increases the signal due to the increase in the Boltzmann factor. However, there are certain ranges which work best for different sample classes. For radicals, for example, it's better not to go to the very lowest temperatures because you may easily saturate your samples, whereas polynuclear metal clusters, for example, oftentimes require really, really low temperatures. Sometimes 4 Kelvin are even too high. But these are just a few numbers. Of course, this is strongly sample dependent and may vary, but just when you are starting an experiment, this may help planning your experiment. I will not go much into detail about quantification of spins. However, I would like to mention this, and even if you are mainly interested in the spectral shape or line shape analysis of your EPR spectra, in many cases it's very useful to do a spin quantification, because EPR is very sensitive to many paramagnetic states. However, samples which are either not paramagnetic or maybe EPR silent, this is a bit of a weird term which I will explain later. These are high spin systems which are paramagnetic but difficult to detect, may be overlooked, and therefore relating the number of spins in your sample to your sample properties, like for example the amount of a certain metal which you have in your sample, is oftentimes useful. You are doing spin quantification in the following way. You detect your EPR spectrum, then you are doing a numerical double integration, and then you plot the double integral on a calibration curve which gives you the number of spin or the spin concentration in your sample. This works for certain sample classes super well, like for example nitroxides and radicals. For metals it's sometimes difficult, and but for the details I would advise you to look into the book by Gareth and Sandra Eaton, which covers most cases which you may encounter. Basically, just as a spoiler, the main challenge is to get a good calibration curve. This integration may work, however, you have to relate your spins to a reference samples, and they are often not easily available. Now we are coming to line shape analysis. You got already pretty much exposed to this equation. Nevertheless, I will walk you once more through. You know about the electron-Zeeman interaction, which couples the electron spin and to an external magnetic field. The zero field splitting for spin larger 1/2. The nuclear-Zeeman interaction, I think, was not much introduced today, because in many magnetic spectroscopies it's only a minor contribution, but it may be important in double resonance experiments. The quadrupole interaction is the equivalent to the zero field splitting for the it couples nuclear spins to each other, again with a nuclear spin larger than E1/2. Hyperfine interactions are a super rich source of information in magnetic resonance. This is the coupling between the electron spin and the nuclear spin, parametrized by the hyperfine tensor, and in addition spin-spin couplings. I've already somehow mentioned this, but the interactions, the energy ranges or the resonance frequencies of these interactions can vary over a very wide range. For example, quadrupole interactions can be in the kilohertz range, or small hyperfine couplings, whereas zero field splitting goes up to, Dan has shown an example of 100 reciprocal centimeters, which is somehow related to many terahertz. I don't know, 30 would be approximately 30 terahertz. So you can have very large ranges, and this is important to know, because the proper choice of the magnetic resonance experiment depends on what you are after. And this will be actually the rest of my talk, to show you a few examples what methods you can apply to extract particular interactions from your sample and relate them to the properties of your sample. This has been already also said by Dan and Frank. The G factor of the free electron becomes a three-dimensional property called G matrix in a molecule, and this depends on the electronic structure of your molecule or paramagnetic specimen, and this tensor is oriented on the molecular frame of your sample. However, how it is oriented on the sample is sometimes not. In some cases, one can just see this more or less by looking at the samples, but oftentimes this is complicated how it is oriented. But it has very important consequences for the spectroscopies which we are applying, because now our Zeeman interaction depends on the orientation of the molecule or specimen with respect to the external magnetic field. This can be shown here with such an ellipsoid, where the main values are shown here on the x, y, and z axis. This would be, for example, an axial case where gx and gy are approximately the same, and gz differs. And this thingy here is then oriented with respect to the external magnetic field, and this changes the resonance condition in the following way. This is again the resonance expression for the axial case, which is shown here. And this term determines the energy splitting, and therefore if we change the orientation of our molecule and thereby the tensor with respect to the external magnetic field, we shift our resonance line. This has been employed from very early on to determine information about transition metals. Here again is shown the structure of myoglobin, and this is an experiment which Ingram and Kendrew, who later received the Nobel Prize for determining the structure of myoglobin, here somehow a bit lost in his model of myoglobin. They had these crystals available which they needed for X-ray crystallography, and did an EPR experiment where they oriented the crystals with respect to the external magnetic field and got this angle dependence of the resonance line. So these are the G values. Here's G equals 6. We will come to this later. But this is therefore probably taken from methmyoglobin, iron 3 in S equals 5 half state. And by changing the orientation of the crystal in the spectrometer, they got these curves, and from these curves they could determine the orientation of the cofactor in the protein before the crystal structure was determined. You see this is already published in 56. And this was then an important example, and is still, I think, a very beautiful example how the G tensor can be employed to derive structural information in this case. There are a few paradigm cases. Oftentimes two G values are the same. These are called the axial cases, and depending whether the smaller two values are the same, the ones which are the same are called G perpendicular, and the one which is left is called G parallel. If G perpendicular is larger than G parallel, the spectrum looks like this, and this is the derivative, and this is the opposite case. If all three components are different, we get a rhombic pattern, and this is and this looks like this. Shown here is not now are cases where powders or frozen solutions are measured. This means all orientations of our molecule, here denoted by these single peaks, contribute to our spectrum, and then showed an example how such a powder pattern can be determined, because different orientations will contribute different to our spectrum. The canonical values are very useful because these are the turning points here and here. From this we can directly read off our main values. However, in order to interpret the spectrum, powder average has to be done with many diagonalizations of the spin Hamiltonian, and there are different ways to do this, and we will play around a bit with this tomorrow in our EPR simulation tutorial. An additional case which I left out up to now is liquid solutions, because in liquid solutions, in particular in the so-called fast motion regime, when our molecule tumbles fast, all the anisotropies are averaged out in our spectrum. We just get the isotropic G value, and if sufficient hyperfine coupling is present in our sample, we also see the isotropic hyperfine couplings. This can be very nice and useful because when combined with it, oftentimes it's a very clear signature of a particular radical, for example, and having the isotropic values and the anisotropic values is oftentimes necessary to determine also the signs of the hyperfine coupling. Yeah, now we switch on the hyperfine coupling. In a very simple case, this is S equals 1/2 coupled to a nuclear spin E 1/2. And this leads to the following energy level diagram. This is our EPR transition without any coupling, but in the presence of an external magnetic field. And then we couple the nuclear spin to the electron spins and get the following orientations of the spins with respect to each other. I denoted this beta and alpha spins. Beta is the electron spin, which is down, and the nuclear spin up, and then beta down, beta electron spin down, nuclear spin down, and so on and so forth. Important is that the hyperfine interaction modifies the energy levels, and this leads to a splitting of our EPR spectrum, which can be calculated by this equation. And the number of splittings is directly related to E. This is the nuclear spin. So since we have a spin E 1/2 here, we have two lines. But if you would have E1, then we would have 3, and so on and so forth. I mentioned, and you heard this today already in the spin Hamiltonian introduction, that hyperfine couplings have an isotropic part and an anisotropic part. The anisotropic part provides information about the orientation and the distance of the nuclear spin and the electron spin with respect to each other, and can be, in many cases, described by a dipolar term. It's orientation dependent because the relative orientation of this pair with respect to the external magnetic field will determine the size of this. It will determine the resonance position. In addition, there's an isotropic part. Oftentimes, this can be directly related to the probability density of the unpaired electron in the s orbital, and therefore isotropic hyperfine interactions carry important information about the electronic structure of a molecule. But I think Frank has described this already in more detail today. Important, there are many different magnetic isotopes. Not all of them are magnetic. Many isotopes have E0, but the nuclei, which are really abundant, fortunately, have nuclear spins, like, for example, protons. This is the basis for all the MRI imaging. Also deuterium. Carbon, somehow a bit unfortunate, has only a very low abundance of magnetic 13C. Nitrogen has a nuclear spin, but also many important transition metals, like, for example, manganese, vanadium, copper has 2 isotopes. We will talk about this a bit later, or molybdenum, and many others. And these different spins and different gyromagnetic ratios lead to particular interactions which can be measured, and oftentimes can be just more or less directly read off from the spectrum. Here is the case of an oxygen vacancy in titania. And if you look at the spectra, you see here clear splittings, a very large peak in the center, but the intensity of these peaks differs through the spectrum. And this can be straightforward rationalized by the fact that titania has is mainly 3 isotopes. The most abundant has no nuclear spin, but there are 2 with approximately the same abundance, and they have different spins. Therefore, we have now here 1, 2, 3, 4, 5, 6, 7, 8. 8 exactly. 8 lines, and this directly tells us that we are probably dealing with an E plus 2 multiplied E plus 1 system, which is 7/2. In addition, we have here these additional peaks, and they are a superposition of titanium 47, which has only 5/2 with the 94 titania, and this then already gives us a clear indication where the electron spin is sitting, that it is delocalized over the titanium atom, and the size of the hyperfine coupling is what carries significant information and can be calculated, for example, in quantum chemical calculations. What is also clear from this spectrum that each electron spin couples only to one nuclear spin in this case, at least only one resolved nuclear spin, because the spectra simply add. It's not that the electron spin couples to two different isotopes, but mainly to one. This is, in the most general case, not the case. Electron spin will couple to many nuclear spins, and then things get a bit more complicated, because then the splittings in the spectrum increase in a multiplicative way. This is our term, which determines the number of splittings originating from the nuclear spin. And if we have now n different nuclei, everything gets a bit messy. If we are dealing with equivalent nuclei, for example, here in the case of a methyl radical, which has 3 hydrogens, the number of lines and their intensities can be determined by a Pascal triangle. For example, here we have 3 hydrogens. They have spin 1/2, and we have to go, this is 0, 1, 2, 3, and this is our pattern 1, 2, 3, 2, 1. Methyl radicals are a quite interesting case, because they mainly carry spin density here in the on the carbon. However, this carbon spin density leads to negative spin density on the hydrogens via spin polarization. We are now dealing with 2 different cases: anisotropic G matrices and anisotropic hyperfine couplings. However, in particular in transition metals, we have typically both. And shown here is an example of cobalt-2 in an hexaquo complex. This is an octahedral crystal field, which splits the d orbitals in an EG and a T2G manifold, and the axial elongation further splits or lifts the degeneracy of the orbitals and leaves just this, and we end up with 1 unpaired electron here. This axial case is reflected by an axial zerofield splitting and an axial hyperfine coupling, and this is the spin Hamiltonian, the electron-Zeeman interaction, the copper hyperfine coupling, and the other nuclei which we neglect for the moment, and the eigenvalues are given by this equation here. And if we calculate a powder pattern or measure an EPR spectrum of such a complex, we get a spectrum which looks like this. And this has 2 characteristic peaks which are originating from this rather large, the values are not given, sorry, from this rather large G anisotropy. And on top of the G tensor anisotropy, we get in addition 4 peaks. And these 4 peaks are originating, since we are dealing with copper, we have E3 and this leads to SE plus 1, 4 peaks on top of our G parallel component. The same is true for the G parallel, but since the same is true for G perpendicular, but since the hyperfine coupling is much smaller here, it's not resolved. But we will learn about techniques how even these can be determined. Well, here in this case we have a super nice G-tensor resolution. However, in many cases, in particular for radicals, the G-tensor is not resolved in the so-called X-band spectrum. X-band is the frequency which we usually use in EPR spectroscopy. And then one possibility to increase the resolution on the in the spectrum is to increase the external magnetic field. This is shown here schematically for the case of a sample which has two absorption lines with close-lying resonances because of close-lying G values. And if we increase the external magnetic field, the resolution increases if we assume that the line width of the sample stays the same. This is often the case because one of the most important line broadening mechanisms we are dealing with, at least in liquid solutions, is unresolved hyperfine coupling with these zillions of protons in the environment. However, sometimes there are also field-dependent line broadenings involved, and then they destroy all of this. These are the frequencies which are used and commercially available for EPR spectrometers. This is the energy corresponding to these frequencies, and these are the resonance fields at G equals 2. I think 90% of the experiments are done at X band and probably another 10 at Q band, and the rest of 90 plus is, but nevertheless, high frequency EPR is in some cases indispensable. An example is shown here. This is the FRD radical cofactor in glucose oxidase. This is a protein, and at X band frequencies, the EPR line has very little structure. If we increase the external magnetic field now here to 360 gigahertz and something like 13 Tesla, we can clearly resolve our G tensor, and in addition also increase the hyperfine resolution, because since we separate now our hyperfine couplings on different G components, oftentimes the hyperfine resolution increases too. There is another case where increasing or varying the resonance conditions is indispensable, and these are cases where the magnetic interaction parameters are in the either weak field regime or in the intermediate regime. And what we mean with weak field and strong field regime is that the interactions, in particular, for example, Zeeman interactions or hyperfine couplings, are large compared to our field. This is then, the field is then weak, it is not strong enough and this oftentimes complicates EPR spectra. An example is shown here for an S equals 1 bismuth radical with a nuclear spin of 9.5 with quite pathological G values, and this together with the very large hyperfine couplings lead to a situation where in the low field regime, where at X band frequencies we are in the weak field regime, and therefore the excitation energy which is available in our spectrometer only excites few transitions, and without any further information this is nearly impossible to assign them to this energy level diagram. However, if we move to higher frequencies, in this case 10 times higher, we can again nicely resolve our GZ, GY and GX component. The spectrum is still very busy because of our 2E plus 1 10 lines on each component, but this is the simulation, but the measured spectrum of this case looked nearly as good, and was in this case the basis for assigning these hyperfine couplings and setting the basis for more thorough characterization with quantum chemical calculations. What time is it now? Oh yeah, okay. Up to now I've only spoken about S1 half systems, but in transition metals, of course, and you have heard this, Dan talked about this in great detail, high spin systems are of great importance, and even the normal case shown here is again iron 3 in an octahedral field, which leads to where the 5 electrons are evenly distributed in the d orbitals. However, if we change the ligand field, then we reach a point where it's energetically more fortunate to place 2 electrons in one orbital, and then we get low spin states. With more complicated coordination structures, we can of course have also intermediate states, but these high spin states have special properties. I selected here a few examples. This is kind of EPR transition metal table because it distinguishes into half integer and integer spin states. I will come to this in a second, just to tell you what is depicted here. This is the filling of the d orbitals. This is the distribution of the electrons in an octahedral field in the low spin and in the high spin states. This is the resulting high spin and low spin values which you get, and these are the ions for which these cases are valid. In EPR, EPR is very powerful in detecting half spin states. They are called Kramers states. However, integer spin states are oftentimes much more difficult to detect, and this is due to the zero field splitting, which has been also already introduced by Frank and Dan, and this is the interaction for spin 1/2. It's a multipole effect. It's the interaction of electron spins with themselves, and this is a matrix again, which is arranged such that dz has the largest absolute value. This is the matrix is traceless, and it's diagonal in its principal axis system, and these are the conditions under which one can rewrite this matrix such that the whole matrix can be described by only 2 values, an axial term d and a rhombic term e. In the axial case, like for the G tensor, 2 values are the same, and in the if you have an additional rhombicity, then all 3 values are different. And now, why are they so different? If we assume, for example, an S equals 1 state with 3 ms levels, 0 plus minus 1, axial zero field splitting lifts the degeneracy such that plus minus 1 remain twofold degenerate. I think Dan had the similar picture, just other way around with the negative d, but both is possible. And if we then also switch on a rhombic term, the degeneracy is fully lifted. And this means that if we apply our continuous wave EPR experiment to such a case, and our microwave energy is not high enough to excite transitions between these states, the sample will be EPR silent, despite it is paramagnetic. And therefore, integer spin states are not so much liked by EPR spectroscopy. However, this is of course wrong, because they are paramagnetic, and under certain one has to modify the resonance conditions to make them detectable. The situation for Kramers systems is different, because here are again the 4 ms levels, which are degenerate without zero field splitting. Zero field splitting lifts the degeneracy between the in this case lower lying ms plus minus 1/2 and ms plus minus 3/2, and they stay degenerate even if we have a rhombic term. And this allows us to split these levels by an external magnetic field and drive transitions between this, and therefore Kramers systems in most cases are detectable by EPR. There are some cases for negative zero field splittings where low temperature EPR and the detection can be difficult. However, Kramers are much simpler than non-Kramers. This is the take-home message here. I skip this because Dan has already shown it. This is just an extension of this scheme here to higher spins. I would now like to mention something which has been already mentioned in Dan's lecture today, but is very important in EPR, and these are these so-called effective G values. Shown here is again the methyoglobin spectrum of the methyoglobin of the heme cofactor, and this is a very axial system, gives a super nice axial spectrum with an G value above 100 millitesla and one around G equals 2. And this is often called G effective 6. This is slang which you find in many labs. And this is coming from the fact that such a system can be calculated by assuming, I'm switching here, such a system can be calculated by assuming an, I call it effective spin, then today called it fictitious spin, whatever effective is very commonly used, and calculate the EPR spectrum with an S equals 1/2, assuming an S equals 1/2 and modified G values. And our zero field splittings are now squeezed into these G values. We still have, for this case, true G values, which would be here Gx and Gy, which are very close to the free electron G value of 2. So if you do a calculation of the spin Hamiltonian parameters for such a heme, you would get G values around 2. But when you measure, then you get your values which are determined in fact by the zero field split, which are originating from the zero field splitting, and they can be added to the G values that we end up with these effective G values, which are here 6 for vanishing rhombicity, and if we have a bit of rhombicity, the G value is modified and G parallel stays G equals 2. Why is this sometimes convenient? Well, from measuring EPR spectra and from measuring these effective G values, one can estimate the rhombicity of the zero field splitting. I plotted this here for vanishing rhombicity, where we get G effective equals 6. And if we now switch on, sorry, I have to tell you what this is actually. This is plotted the effective G values of the plus minus 1/2, 3/2, and 5/2 levels versus the rhombicity. So this case is here with 0 rhombicity. We now allow a bit of rhombicity, we would be approximately here, and then our spectrum starts to split. Or in other words, if you would measure this and read off the values here, you get information about the rhombicity of the zero field splitting tensor, and this gives you information about the electronic structure of your system. And another case which is even more abundant than this G equals 6 value is G equals 4.3 signals. Some spectroscopists call this shit iron, because this is oftentimes unspecifically bound iron, which, for example, in biological samples, oftentimes appears. And a bit unfortunate is that it can be very intense. And if you see such a signal, you should also look left and right, because maybe you're overlooking the important component of your iron spectrum, because you are blinded by this super immense G equals 4.3. But this is now getting even a bit anecdotal, and I will switch again to the integer spin states. In the strong field regime, I already mentioned what strong and weak field regime is. We are now not talking about a field which is strong against the hyperfine interaction, like in the case of the bismuth, but a field which is strong as compared to the zero field splitting, and these are our 3 levels. And as long as the zero field splitting is small compared to the Zeeman interaction, S equals 1 is by far not EPR silent. There's lots of literature, very nice spectra of triplet states. For example, organic triplet states, and they are oftentimes, if the resolution is good, they are even very easy to interpret, because from the peaks originating from these transitions between the different orientations of the zero field splitting tensor with respect to the external magnetic field, one can, from the powder pattern, directly read off D and E. So everything's cool, and it's not more difficult to measure than S equals 1/2. However, if we now switch to the weak field regime, we enter this case which I have already mentioned, namely that our energy which we apply in the spectrometer may be not sufficient to drive transitions between the MS levels, which are here bent as a function of the external magnetic field. And these are cases which are even pretty important in many cases, like manganese 3, iron 3 is such an example. This would be not a triplet, but it is S equals 2, but the same holds true for it. Cobalt 1, they all have oftentimes zero field splittings which are above what is easily accessible with standard spectrometers. And even high field EPR oftentimes gets to its limits for these states. And in these cases, the most powerful approach is a combination between squid magnetometry and high field EPR. This is what I think has been established as the best method, because squid magnetometry, as Dan outlined, gives you a very nice overview over your system, and if you can then validate your parameters which you're assuming in your squid simulations with resolution in an EPR spectrum, you can be pretty safe that your fits are reasonable. However, as I said, there are limits of this. Here shown again is an S equals 1 triplet state with a zero field splitting of 10 reciprocal centimeters. This is not super large actually. Here are the spin energy levels as a function of the external magnetic field, and I have drawn, I hope one can see this with this beamer. This is the triplet EPR spectrum taken at 700 gigahertz. It's already a very high frequency, but still accessible. The problem in this case is rather the field. I don't know if you know about the availability of external magnetic fields, but even at high magnetic field facilities like in Tallahassee or in Dresden, 30 is pretty much the edge. And therefore, for these cases, it may be fortunate to sweep not along the field axis. If you cannot sweep far enough, for example, in this case of 100 reciprocal centimeters, it's hopeless. The spectrum would be here somewhere. But along the energy axis, and this can be done with, for example, a combination of IR and magnetic fields, and then we are driving transitions like the same EPR transitions from MS0 to plus minus 1, and the spectrum which we are getting is centered around D and is split by the rhombicity of by the rhombic term of the zero field splitting. And these ranges which I'm showing here are currently somehow the edge of what is experimentally possible. Up to now, we were dealing with interactions which were pretty well resolved in the spectrum, or where we even had problems to make our spectroscopic window broad enough to really cover the interactions, like in the case of these immense hyperfines which I have shown, or a more frequent encountered case, large zero field splittings. This makes our transition energies large. We need large fields and large frequencies. However, a lot of information is also contained in small interactions, and this is in particular the hyperfine interactions, the quadrupole interactions, and the electron-electron dipole interactions. And they are usually covered by the line width of the EPR spectrum. Shown here is an example of such a small nitroxide molecule, which is frequently used as spin label, but this is not so important here. Measured at W band, which is 95 gigahertz, and these are simulations assuming two different Gaussian line widths, and the most dominating term to the Gaussian line width is coming from this equation here, which I have already introduced. This is the multiplicative broadening of the spectrum by coupling to many magnetic nuclei in the vicinity, and in most cases this is just hydrogen. Hydrogen is everywhere, has a pretty large gyromagnetic ratio, gives good splittings, and this broadens the spectra a lot. And then here, for example, these 1, 2, 3, 1, 2, 3, 1, 2, 3 lines would be the hyperfine coupling of the nitrogen, and even so there is a lot of spin density sitting here on this NO fragment. Oftentimes in the spectrum this is not resolved, and but we want this pieces of information because they tell us, for example, about the coordination structure of a transition metal, and therefore we have to extend our experimental repertoire to resolve small couplings in our EPR spectra. This is usually done by changing the detection technique a bit, and requires pulse techniques. In the last 25 minutes, which I now still have, I would like to talk a bit about pulse EPR and how it increases the resolution in EPR spectroscopy. The motion of the magnetization, which is formed by the individual spins in the samples, so you have many spins and they align with the external magnetic field and lead to a magnetization. Here in our case the external magnetic field would be oriented along Z, and the motion of the magnetization after excitation can be described by these set of equations, which are the Bloch equations, and you have the elements of the magnetization mx, my and mz. Then you have the Lamor frequency, and in addition two values which are called here T2 and T1, and these are the spin relaxation times. This is the time when we deflect our magnetization from equilibrium. It needs to go back to equilibrium, and there are two different kinds of relaxations. One is the T1 relaxation back to the Z direction, and the T2 or phase memory time is the relaxation in the XY plane. I understand that this is a picture change. If you have questions, please ask me at the end of this 20 minutes, but moving our magnetization is now necessary to understand what our pulse experiment is doing, and I hope I can show this here by again referring to free induction decays. As I have already mentioned, in order to generate a free induction decay, we put our sample in an external magnetic field, apply hard microwave pulse, and then let the system relax. And it will relax and emit radiation, and this is our decaying magnetization. And what happens on our Bloch sphere is that we applied a pulse which is called pi half pulse, which means 90 degree. We flipped our magnetization 90 degree from the orientation along the B0 field in the XY plane. And now, due to the fact that the different spins in our sample see slightly different local fields, because each spin may have a slightly different environment, they have slightly different Lamor frequencies, and these different Lamor frequencies make the signal dephase in the XY plane. One is faster, one is slower, and therefore this net magnetization vector gets shorter, which is just the decay of this signal here. However, as I already told you, we cannot do this. So, because our detection is not fast enough. But we can do something else, and this is creating so-called spin echoes. A spin echo works in the following way: we again flip our magnetization in the XY plane. In the XY plane, it dephases and creates an FID. This is not shown here. This FID would be here. And then we apply an additional pulse, which is a pi pulse, which flips the whole pancake 180 degrees. And if you now think about a horse race, where the fastest horse is in front, suddenly it will be the last. And at a certain moment, namely exactly after the pulse separation time tau, all the spins are in phase again and lead to the emission of an echo. And this is separated from the excitation, and therefore can be measured much more easily than a free induction decay. And this technique was introduced by Erwin Hahn. This sequence is also called Hahn echo sequence. Is the basis for many experiments, and paved the way for a really rich field of magnetic resonance applications. In EPR, there's another challenge which I mentioned, but you might not be fully got it. You might not have fully gotten it. In NMR, we can make our RF pulses short enough to excite our whole spectrum at once. In EPR, our so-called excitation bandwidth, this is the inverse of our pulse length, is oftentimes not sufficient to excite such a whole spectrum. Instead, we are just burning a small hole into our spectrum. In order to get the full pulse spectrum, we therefore have to apply such a pulse sequence at different points of the external magnetic field, integrate over our echo, and then we plot it versus the external magnetic field. This is an field-swept echo experiment. This is more or less the same as the CW spectrum. It's just if you integrate your CW spectrum, you get again the absorption shape of the spectrum. However, these techniques give you direct access to the spin relaxation time, because if you vary the pulse separation time tau between these two pulses, your echo will become smaller, and if you plot this versus time, you directly get, for example, the phase memory time, and you can do similar things to get the longitudinal spin lattice relaxation time T1. It's just a slightly modified pulse sequence. Now we switch back to our simple case of an S equals 1 coupled to a nuclear spin, and I'm switching back to this picture because what I would like to show you in the next slides is how a combination of EPR and NMR can be used to resolve these small hyperfine couplings which are covered under, hidden under our line widths. And I've shown this already. This is the EPR transition. In addition, we can also, if we have nuclear spins, we can, of course, they're exposed to an external magnetic field, and if we apply radio frequency, we can also flip them. And if we couple the two spin systems, we get the level scheme which we have already seen before. There is a bunch of so-called allowed transitions, which are the plus minus MS1 transitions and the delta ME0 transitions. So we are only allowed to go from here to here and from here to here, nominally. And there are allowed NMR transitions. And if we draw this as such a 4-level scheme, this would be this level, this one, then they are connected by more or less allowed and forbidden transitions. These are the NMR transitions, this is an EPR transition, and these are cross-relaxation pathways which are needed for, which can be also exploited to determine the hyperfine couplings, but I will only very briefly touch this later. Now back to our electron spin echo sequence. This would be our 4-level scheme. We at low temperature we have most of our polarization here in the lower energy levels, and if we apply a microwave pulse, we invert the polarization, and this leads then to an echo. If we now modify our pulse sequence, we have our echo sequence, and this is our 4-level scheme, and the echo inverts this polarization here. What we are doing now, this is preparation to get finally our double resonance, is that we apply a so-called pi pulse in the beginning. This pi pulse moves all the polarization here, and we can read this out with our echo sequence here. So this is the preparation pulse, we just wait a bit, and then we read this out. And if we get now the same echo, but with a different phase, since the polarization is opposite, we are doing phase-sensitive detection. Our echo has now a negative sign. It's not, for the moment, it's not super useful. However, what we are now doing is now we combine electron paramagnetic resonance with nuclear magnetic resonance by applying a resonant radio frequency pulse, which is in resonance with one of the NMR transitions. So, once more, we prepare, we invert our polarization, and then this RF pulse shifts polarization from this level to this level. And if we now detect on this level, on this transition here, we will have a reduced EPR signal because our spin population is gone. There's no spins anymore which we can flip because they have been shifted to here. And therefore, our echo will be smaller. And if we now repeat this sequence by changing the frequency of this radio frequency pulse, we are moving in and out of our NMR transitions and can record this by changes of our spin echo amplitude, and this gives us the NMR spectrum of the nucleus which is coupled to our electron spin. And even we can, this is such a spectrum, it's plotted versus a radio frequency, of course, because we are sweeping the radio frequency. This would be an X-band Endor spectrum. These spectra are centered around the Lama frequency, therefore one can guess already that this is a proton because the proton Lama frequency is roughly 15 megahertz at X-band. And this Peak pattern here is just determined by the parallel and the perpendicular part of the hyperfine coupling. And this is super selective because we do it on a, since we select the radio frequency and either excite protons or, for example, nitrogens or O17, we can selectively measure all of these interactions and get the information which is otherwise hidden in our spectrum. And there was somebody who asked me about, are you sure that the hyperfine tensor and the G tensor is always collinear? And of course it's not. This is, in this case of this Higgs-Aquo complex which I have shown, the copper hyperfine and the G tensor are pretty collinear, but in most cases, like for example here, this is an iron sulfur cluster, and here is, I think it's a proton, yeah, with its hyperfine tensor. Why should it be collinear with the G tensor? But you can determine the relative orientation of this tensor if you are doing so-called site-selective experiments. This is our EPR spectrum. Remember, we are applying our pulse sequence to one of these resonance positions, which are shown here as errors. And we select only a small fraction of the spins which are contributing to our spectrum. This is shown here with these spheres. The yellow parts are the excited, these are dense spheres actually. And the yellow rings are the orientations which we select by our pulse, which we place at different positions of our spectrum. And if we take on these positions then Endor spectra, we can determine the orientation of the tensors with respect to each other. This allows us to not only determine these splittings with very high resolution, but also the relative orientation of them with each other. And this gives us single crystal-like information on the tensors, and is therefore very powerful and broadly used. I have only introduced one pulse sequence for the sake of time, which is Endor, electron-nuclear double resonance. This is, as I have said, a combination of microwave and radio frequency pulses. You just do an NMR and an EPR experiment combined with each other. This covers a very broad range of coupling strengths. Of course, you are choosing the nucleus which you are measuring by choosing the radio frequency. You can resolve narrow lines. Here's a nice example of an hydrogen Endor on the cofactor and ribonucleate reductase. It's very orientation selective, as I have shown, which is sometimes wanted and sometimes unwanted, and the sensitivity depends on the strength of the coupling. There's another technique which requires only microwave pulses. This is called electron spin echo envelope modulation. I have shown you this sequence where you have two pulses, and if you increase the pulse length, then your echo is decreasing. I said this, and I hope you remember. But in fact, on top of this mono-exponential decay, you also see oscillations, and they are coming from nuclear coherences, and you can Fourier transform such decays and get a spectrum which is ideal for to detect small hyperfine couplings and narrow lines, but these coherences only appear under certain coupling conditions. Therefore, this is very powerful, but not applicable in all cases. It is also very widely used as a two-dimensional technique, which is called high-squared. Here's a very nice example of a high-square experiment on copper, where the hyperfine coupling of this hydride was determined. There's a third method, which is called electron-detected nuclear magnetic resonance. Is only also only based on only microwave pulses, and this has the advantage that you get the whole Lamour spectrum in one spectrum. This means in one shot you get nitrogens, protons, and everything else which is coupled to your electron spin. It's very sensitive, so also a very powerful technique. However, since its resolution is limited as compared to eSIM and Endor, and it's very good if you have broad lines and you don't know where they are. For example, here is the case of O17, or for example manganese spectra, where you don't know where the manganese couplings are. Then it's a very powerful technique. However, if you are going for a resolution like this, better use Endor. These are only hyperfine spectroscopies. There are other pulse EPR techniques, and there are two books which, if you are interested in this and you would like to learn more about it, two books which I can really recommend. One is written by Gunnar Jeschke and Arthur Schweiger, which is called Principles of Electron Paramagnetic Resonance, and there's a textbook edited by Daniela Goldfarb and Stefan Stoll, where different EPR methods are described in quite detail. It's a bit more recent, but also Gunnar's book contains still a lot of wisdom. And in addition, I suggest here a few books which I found useful while trying to learn EPR. There are different EPR simulation programs. I listed it here Stefan Stolz Easy Spin homepage as further reading, because the description and the literature and the insight you get from on EPR just by reading this homepage, I also found quite useful. The school is still not over. We are on Wednesday, and there will be more about EPR tomorrow and also on Friday. We do a tutorial tomorrow on the simulation of EPR spectra. I will repeat a few things, and if you have questions you would like to try out, we uploaded a program for the simulation of EPR spectra. It's actually based on EasySpin, but the advantage is that you don't need MATLAB, you just need a runtime library. And this runtime library is also on the page. But I would really like to ask you to download this library and install it on your computer if you want to take part in the tutorial, but because it will strongly limit us if you don't have this available tomorrow. I will be 15 minutes earlier at the room where the tutorial takes place, in case you should have problems with the installation, but please give it a try on your computer, because if everybody shows up, then we may run into problems. I expect that you have the program already installed on your computer and started when we start the tutorial, and if you have problems, just join us tomorrow morning. There is an additional tutorial on the calculation of EPR parameters by Dmitris Pantazis and his co-workers, which shows you how the parameters which you extract from your EPR spectrum can be actually related to chemical information and structural information. And we do a lab tour on magnetic characterization techniques, including Mössbauer, squid magnetometry, and also EPR on Friday. I'm showing the faces of all of these tutors, because you're of course very welcome to approach all of us if you bump into one of us, or just look for us around here or during the lunches, coffee breaks, and so on. And with this, I would like to thank you for your attention, and thank you for staying till 6 o'clock in the evening.